Hello students, welcome back. The final topic for lesson 11 revolves around the integral constant plus c. How to deal with it. Here's a motivation example problem. Let's begin with the derivative function f prime of x and find out the original function f of x through the antiderivative computation like this. Or if you prefer, you can start from the original function lowercase f of x and find out its antiderivative function capital F of x. Either way, it's the same. Same integral problem, same integral constant plus c. Now, how do we deal with this? This plus c will give me infinitely many solutions because the c can be anything, but I don't like infinitely many solutions. I'd like to bring it down to just one solution. How do I do that? One way to handle it is to use so-called initial condition. Here's an example. I just highlighted this f of 0 equals to 0, and this is an example of initial condition. Initially, at time 0 or at x equal to 0, the function value is 0. Does it help? Yes, it does. Let's begin with this. Copy and paste this antiderivative computation. And let's apply this initial condition. F of 0 is 0 squared plus c, and that's 0. And from here, I can find out what c is. Where did I use this initial condition? Right here. And consequently, I get c equal to 0. So let's go to the answer. This is supposed to be plus c, but c is 0. So same as plus 0, and nobody writes it like this. Plus 0 just goes down to just x squared like this. Consequently, we do not have arbitrary constant anymore. We have a unique solution. Here's another example. Same problem, same derivative, same antiderivative computation, but we have a bit different initial condition. F of 0 is -1 right now. So how do we handle that? Well, let's copy and paste this entire thing. Okay, starting from here, let's see. F of 0 is now -1. And consequently, c is -1. This is supposed to be plus c, but c is -1, so plus c is same as subtracting 1, and that's how you get the unique solution. Here's still another example. Let's see, most of the time it makes a lot of sense to start from 0 because that's a starting point. Right now, what value we have, but in some case, I want to use yesterday's value, so f of -1 is 3. That's perfectly legitimate. And how do I solve that? Let's copy and paste this entire thing because we are doing the same antiderivative computation, except that this time f of -1 is 3, and that corresponds to the red condition. So what is the c value? 3 minus of -1 squared, which is +1, so it's 2. So the answer is supposed to be x squared plus c. Yes, we have this antiderivative computation, but plus c is same as adding 2. So we end up with plus 2, and there goes the unique solution. Does it make sense? So same problem, same antiderivative computation, but you can get different final answers due to different initial value condition or just initial conditions. This kind of problems are called initial value problems. Let's go to some real problems. And this time, I'm going to leave the antiderivative computation to you. I don't want to get bogged down into that computation, So stop the playback and do the computation on your own. Once that is done, plug in x equals to 1 to utilize this initial condition. Go ahead. Stop the playback if you want. Well, here's the antiderivative computation. And then we want to use this initial condition, right? F of 1 is therefore copy and paste everything here, and in place of x we have 1 to the third power, which is 1, and 1 to the 3/2 power, that 2 is 1. So basically we have 1 plus 2/3 plus c, and that's equal to 1/3, and from here you can solve for c. If you do it right, you're going to get c equals to -4/3. So there you go. Initial condition, so c value. But this is not the answer. The answer is, what is this antiderivative function? What is this f of x? So you have to plug in this c equals to -4/3 right here. That is the final answer. Here's another problem. Again, I'm going to leave the antiderivative problem to you. Go ahead and do that. This is going to be a little bit harder antiderivative problem because you'll have to use extended formulas here. Those relate to 1 over a. You have to undo the chain rule. Okay, suppose that you're done. Here's the antiderivative. Oops. Antiderivative, okay. Power form, anti-differentiation, and then we have simplified answer. But this line is perfectly good. And then plug in x equal to 1/2 here. Let's see. If this is 1/2, 1/2 times 2, so that's 1. 1 plus 3, so we have square root of 4. So you can calculate it. Plug in x equal to 1/2 here, so 2 times 1/2 is 1. So 1 minus 1, so we have e to the 0 power. Again, you can calculate it. So square root of 4 is 2, e to the 0 power is 1, so we end up with this computation. C is -1. That's not the answer. You have to plug in c equal to -1 back into this original computation. That's the final answer. Let's do some application problems. Stop the playback and read through. So what do we have? Marginal cost, the derivative is 3x plus 50. And initial condition, the fixed cost, that is c of 0. When I produce nothing, still I have this cost. So basically it's this problem. C prime of x is 3x plus 50, alright? And then c of 0 is 10,000. So how do you find out your c? It's integral of 3x plus 50. So 3/2 x squared plus 50x plus c, but oh, I don't like the c. I already used up c for cost, so let me find another character. K for constant. And then I can determine k using the initial condition. So c of 0 is, well, plug in x equal to 0 to this guy. That's 0 squared, so that's 0. And that's 50 times 0, so that 2 is 0. So we get k, and that's 10,000. So plugging in 10,000 right here, you're going to get the final answer. Here we go, anti-differentiation, and initial condition, and then final answer. Does it look good? I don't need these anymore. Anti-differentiation, initial condition, and plug in that k. that was a bit too trivial because we got fixed cost. Okay, let's do a bit challenging problem. Oops, wrong cell, sorry about that. Three square root of 2x plus 25, and then C of, this time not C of 0, the cost to make 300 unit. So C of 300 is there. And that's 26,625. So from here we have to find out the total cost function. How do I do that? Well, it's an antiderivative computation, so you have to take the antiderivative of this. Sorry about the typo. 3, and then 2x plus 25 to the 1/2 power. So what do we have? Add 1 to the power. So 3/2 power, and then we have to divide. So what do we get? We just get 2, and then interval constant plus k. Okay, how about this initial condition? C of 300 is 2 times, oh my, looks like you'll have to use calculator for this. So if you want to find out your k value, k is going to be 26,625 minus, well, this value here. And if you do it, you're going to get whatever value. Let's see, 625. 625 is 25 squared. So square root 25 and the third root of it, well, it's not impossible to calculate, but what's the point? Punch this into calculator. And this doesn't look good. Apparently I made a mistake somewhere. Negative 4625. Well, I don't find any mistake here. So I guess that's it. Is this right, really? Or did I make some mistake somewhere? Apparently I did make some mistake here. So what did I do wrong here? 1/2 power, 3/2 power, and then, oh, I see, I didn't take the antiderivative correctly. 3 times 2/3 power, because I have to divide by power, but I forgot this. I have to undo the chain rule. 1/a, that's what I forgot. So 3 cancel out, 2 cancel out. So this is just 1, and this computation is, okay, that makes sense. So fixed cost is 11,000. Fixed cost is negative. That doesn't make any sense. Cost is cost. You don't earn money for doing nothing. So okay, that makes a lot of sense. And as for this, please remember this recurring theme of 1/a, and I just missed it, and that was a real mistake. Sometimes I intentionally make a mistake so that you can find out, but this was a real mistake of mine. You see, it's really common to make that kind of mistake about 1/a, so be careful about those. Okay, that's it for lesson 3, or excuse me, section 3, and I leave the rest of the problems to you.